July 14, 2019. The United Kingdom is locked on to two simultaneous massive sporting events, the Wimbledon men's singles final and the Cricket World Cup final. Inside the National Energy System Operator, or NESO, control room, engineers are bracing themselves for the millions of viewers watching these matches. This animated wave represents the alternating current of the UK's power grid. To prevent blackouts, total electrical supply must perfectly match consumer demand every second to maintain a strict frequency of 50 Hz, staying safely between these red danger zones. When a commercial break hits or a match ends, the UK experiences a massive thermodynamic surge, known as the TV pickup. Millions of people stand up at the exact same moment and switch on highly power-intensive 3-kilowatt electric kettles to make tea. Managing a national power grid during a cultural broadcast means solving a physical equation driven entirely by mass human synchronization. 10 minutes before the Wimbledon kickoff, engineers intentionally over-generate electricity, pushing the grid frequency to a high 50.06 Hz. At 1:59, millions of televisions turn on. The sudden electrical draw pulls the frequency down sharply to 49.99 Hz. Forecasters handle these initial predictable drops by running advanced algorithms. They compare the current day's weather and demand against rolling 5-year baselines, overlaying that data with live media intelligence. A scheduled broadcast can be predicted mathematically, but live, unscripted sports carry the terrifying variable of extra time and penalty shootouts. You can't schedule the exact minute the match will end, making the impending post-match surge an unpredictable threat. The Wimbledon final stretches into a grueling, record-breaking 5 sets. Any pre-scheduled power generation plans the grid operators had are now completely useless. They can't rely on traditional nuclear or gas power stations because those massive thermal plants require hours or even days to spool up. Instead, control room engineers have to watch the live broadcast right there at their desks, ready to react the exact second the final whistle blows. At exactly 18:57, Novak Djokovic secures the championship. 1 minute later, at 18:58, millions of spectators stand up from their sofas and head to their kitchens to switch on their appliances in unison. As we can see on this tracking graph, that synchronized kettle surge hits the grid instantly. At exactly 18:58, the frequency plummets dramatically to a dangerous 49.96 Hz. When consumer demand outstrips electrical supply in a matter of seconds, baseline power generation is simply too slow to help. The grid requires a completely different type of physical intervention. The grid's primary defense against these incredibly fast surges relies on specialized gravitational storage facilities hidden deep inside hollowed-out mountains, exactly like the Cruachan and Dinorwic power stations. When the operators need power instantly, massive underground headgates open. Millions of gallons of water from an upper reservoir rush down steep subterranean tunnels, driving enormous turbines at the bottom. This technology is prized for its extreme thermodynamic response time. These massive pumped storage plants can go from standby to their maximum generating capacity in just 12 to 16 seconds. To counteract the sudden electrical deficit caused by millions of people making tea, the grid harnesses raw, instantaneously released gravitational potential energy. The grid operators deploy those fast reserves, and the frequency begins to stabilize from the Wimbledon surge. But right at that moment, the concurrent Cricket World Cup final enters a completely unplannable state, a historic tie, forcing a high-stakes super over. At 19:33, England claims victory. The tension breaks, resulting in a massive emotional release across the nation. This creates a delayed, highly concentrated demand profile. By 1942 and 25 seconds, the sudden load forces a second severe frequency dip, dragging the grid right back down to 49.96 Hz. To catch this 700-megawatt spike, the system relies on the physical inertia of heavy spinning generators to absorb the shock for the first 5 seconds. Immediately after, another rapid injection of hydroelectric power pulls the grid back up to a safe 50.03 Hz. Absorbing two massive, overlapping cultural events pushed the physical endurance of the grid to its absolute limit. Today, that physical endurance is facing a new complication. As the UK transitions away from heavy thermal power plants toward wind and solar, the grid is losing the physical machine inertia provided by those massive spinning metal turbines. Without that heavy spinning metal to act as a shock absorber, the grid experiences a higher rate of change of frequency. When a sudden demand surge hits, the frequency drops much faster today than during historical TV pickups, like the famous 1990 World Cup penalty shootout. To counter this faster rate of change, the grid operator now relies on modern battery energy storage systems. These massive batteries dispatch power in milliseconds. Major live broadcasts act as real-time stress tests for national infrastructure. Maintaining that 50 Hz heartbeat requires an invisible team of engineers, hollowed-out mountains, and digital-speed batteries, constantly working to outpace the synchronized emotions of the viewing public.